Right, hello everybody. So today's lesson is going to be on rational expressions and binomial expansion, and both are closely linked. So what we'll do, we'll get straight onto it. So a rational expression, so we'll start with an example. And a nice simple example as well will be something like this. So rational refers to the word ratio, which means division. So it's a fraction, basically, like that. So again, ratio refers to a division, so a fraction like this. And it's asking us to simplify that. Now, with rational expressions, the key to simplifying always is to factorize wherever possible. So obsess over factorization. Now, this is a particularly easy one, because with this one, what we can do is just take out a numerical factor from the top or the bottom, or from the top and the bottom. So we've got 3x minus 1. No factors on the top actually checking for it, but on the bottom, we can see there's a factor of 6 lots of 3x minus 1. And then we can cancel out the 3x minus 1s, 3x minus 1 on top and 3x minus 1 on the bottom. But that's not the way I like to cancel out, because I think that often students get cancelling out wrong. Often students, for example, with a fraction like this, x plus 3 over x plus 2, will say, right, I'm cancelling the x's to end up with 3 over 2. And that's really not how it works. The sure way to get factorization right and to get cancellation right is to write it as a product of two fractions, to write this rational expression as a product of two fractions. So I'm going to reorder the way in which I do the multiplication. So the 3x minus 1 on the top, and I'm going to put a 3x minus 1 on the bottom as well, times, and on the top we've got 1 over 6. So convince yourself by looking at that that's correct, that it indeed gives the same answer to times 3x minus 1 by 1 and 3x minus 1 by 6 to get the top and bottom of that fraction respectively. And what we've seen here, we've got this here, a hidden factor of 1. And that's what cancellation is. It's pulling out a hidden factor of 1. And we might as well not actually write that we're timesing something by 1, leaving us with just a sixth. So let's do another. And again, it's all about exaggerating, reordering a multiplication to pull out a hidden factor of 1. That's what cancelling to me really is. And again, that's where a lot of A-level students tend to struggle. So have a go at that one. Factorize it as best you can. Take a moment to do that. Then reorder the fraction. Reorder the multiplications in the fraction so that you end up with a factor of 1, i.e. a number over itself. So that's the top factorized. And the bottom, notice it's the difference of two squares. T plus 4, t minus 4. And reordering that, right, as a multiplication involving two fractions, we end up with a hidden factor of 1 times 3t plus 1 over t plus 4. Hidden factor of 1, we might as well not write that to give the answer 3t plus 1 over t plus 4. And we can extend that to much harder problems. So something like this that I'm about to put on here now. Let's put that one there. So obsess over factorizing these. factorize wherever you can, reorder the multiplication so you end up with hidden factors of 1 being exposed, and just cross them out, because we might as well not write 1 times something. And again, that's what cancelling is. And if you do it this way, it stops you making the daft mistakes like crossing out the t's like that, which often students do, but is wrong. So equals, I notice that first one has a factor of 4 in common. The second one, each term has an x. All divided by, and factorize wherever you can there. So we've got the difference of 2 squares. There's the times on the top. Then that one factorizes to x minus 3, x plus 1. And now again, it's about reordering this to expose the hidden factors of 1. So I can see they've both got an x plus 2 in common. So there's one hidden factor of 1. I can see they've both got an x minus 3. There's another hidden factor of 1. And that seems to be it. Times, and then the rest of it, 4x on the top, over and on the bottom. So we've got rid of an x minus 3 and an x plus 2. So on the bottom, it just becomes x minus 2, x plus 1. So now crossing out these hidden factors of 1, which is what cancellation is, but we often just do it without this level of working out, then conclude with the answer equals 4x over x minus 2, x plus 1. And that's that done. And it can get even more complicated. We could do it with divisions, say. So if I put another more difficult one there, I'll give you a moment to get that done. So remember the rule for, and apologies if I'm patronizing here, the rule for dividing fractions is to flip the second, then multiply. So have a go at that. So I would actually do the flipping first. So that's what it boils down to. And then get factorizing. Take out all the factors that they've got in common wherever possible. Like that. And let's reorder it to make the hidden factors of 1 more apparent. So I can see they've both got an a minus 3 in common on both top and bottom. I can see they've both got a 2a minus 1 in common. An a plus 3 in common. And all I'm doing is changing the order in which the multiplication is performed. Times a squared over 4a. So a few hidden factors of 1 there. Crossing out the hidden factors of 1, we get, and there's still another simplification that can be done. We can actually take out an a over a times a over 4. Convince yourself that that is the same thing as before, to just get simply a over 4. And we're done. Now it's made a little bit more difficult when we're asked to add these fractions together. So let's do an example like that. But again, I think that in questions like this, wherever we can factorize, we should. So adding fractions, as you know from GCSE, is all about getting a common denominator. So with these ones, let's factorize again wherever we can. So we can see that the denominator on this one factorizes to get q plus 3. This one 5q over, and both have a factor of 4 in common, 4q plus 3. And now we know what we've got to times by to get common denominators. So the different denominators here are q plus 3 and 4. This one's missing the 4. So if we times by 1 in this really clever way, if we times by 4 over 4, times the top by 4 and the bottom by 4, the net result is we times it by 1, not changing the value, just changing how it's presented. And this one times by q over q, because it's missing the factor of q that this one has. Again, we're timesing by 1, so it doesn't change the value of the fraction, it just changes how it's presented. Equals, well, times the top by 4, we get 8. Times the bottom by 4, we get 4q plus 3. Plus, and here we're timesing the bottom and the top by q to get 5q squared on top, over, on the bottom again, 4q plus 3 equals 8 plus 5q squared over 4q plus 3. And that's really as simple as it's going to get. So there's a few examples of different things we can do to be able to simplify fractions. I think now what we need to do is move straight on to binomial expansion, because that's really the difficult part. So this is significant binomial expansion because often we might be asked to find the binomial expansion of rational functions. So you'll have a formula in the booklet for binomial expansion that says something like 1 plus x to the power of n equals, and I'm going to slightly change the formula you're given to give the same result, but I want to actually show you where the pattern in this formula is. So the first thing we're going to do, the first term is 1 over 0 factorial, and remember 0 factorial is defined as being 1. So we're not doing a divide by 0 there. 0 factorial is 1, tested on your calculator. Plus n x term to the 1 over 1 factorial plus n minus 1 x term squared over 2 factorial plus n minus 1, n minus 2, x term cubed over 3 factorial, and so on. And this way you can see the pattern emerging, because the power here matches the factorial on the bottom. And we can see each time we add an one less, we multiply by one less than the previous factor. So n, then we get n minus 1, n minus 1, n minus 2. And you're not expected to remember this formula, but the more questions you do, the easier it will become to remember it. So let's apply this now. I should really put the title Binomial Expansion as well, just for clarity of the notes when I upload them. So let's apply this now to finding, let's say, the expansion of 1 plus 2x to the power of, let's say, minus 2. So this time, the x term here isn't x anymore, it's 2x, and the n is minus 2. So we're just using this formula here, given in the formula book, which I've spelled out a little bit more by putting the things in the that aren't mentioned in the formula book on the denominator here. And we're just replacing all the x's with 2 x's. So we've got 1 over 0 factorial plus n times the x term to the power of 1 over 1 factorial plus n minus 1 x term squared over 2 factorial plus n minus 1 n minus 2 x term cubed over 3 factorial, and so it continues. We'll stop at cubed here. Now with the calculator, I think there's a way to make these calculations a lot easier to do. Rather than typing it all in the calculator, the first term's obviously 1, but what I like to do here is count the minus signs before I start multiplying numbers together. So I can see in this whole expression here, there's a single minus sign, which means clearly my answer is going to be a minus. So now I needn't worry about the signs of the numbers. I can just type them in as they appear. So instead of writing minus 2 times 2 to the power of 1 divided by 1 factorial, I'm forgetting about the signs altogether. I'm just going to type 2 times 2 to the power of 1 divided by 1 factorial. Now, actually, in an exam, I wouldn't type something, that should be a divide. I wouldn't type something so trivial as this. I can see, obviously, the answer is 4. But I'm just for illustrative purposes, I'm doing it now. Okay, so again, count the minus signs. I can see I've got 1, 2 minus signs. So clearly the answer is going to be a plus. So let's type this in the calculator now. So 2 times 3, remember I've dealt with the minus signs, so I don't need to deal with them again, times 2 squared divided by 2 factorial, which is 12, plus 12 x squared. Count the minus signs, 1, 2, 3 minus signs there. Clearly 3 minus signs make a minus. I've dealt with those. So I can just put the number straight in the calculator. 2 times 3 times 4 times 2 cubed. The 2's in a cube bracket. Divided by 3 factorial. Which gives me 32 minus 32 x cubed. And so on. So let's do a slightly more difficult example now. Let's do one with a negative sign in the bracket. So let's do 1 minus 1/2 x to the power of 1/2. So I should say that this is different from the binomial expansion you learned in first year, simply because the powers now can be non-integer or negative for that matter. So you only did positive integer powers in first year. Here we've got a fraction and here we've got a negative power. So take a moment, you have a go, and I'll fill in the gaps in a moment, see if you can deal with that one. And I think this level of working is necessary, prevents mistakes. Plus n x term, which this time is minus 1/2 x over 1 factorial, plus n minus 1 x term squared over 2 factorial, plus n minus 1 n minus 2 x term cubed over 3 factorial. And just this bracket here, I can see I've forgotten to put the x in, so I'll go back and do that now. I should say minus 1/2 x squared. There we go. Okay, so the first term again, 1 over 1 is 1. And count how many minus signs there are. You can see there's just one minus sign, which actually makes that a minus. There we go. And 1/2 times 1/2 is 1/4. That was easy enough to do in your head. Let's count the minus signs. So there's 1, and this is a square bracket, so that counts as 2. 1, 2, 3, 2 minus signs in that square bracket. So there's 3 minus signs altogether, which makes a minus. And let's put it in the calculator. So you could type 1/2 in the calculator. However, I'm going to type 0.5 just because it's quicker. So 0.5 times 0.5 times 0.5 squared divided by 2 factorial is 1 over 32 x squared. Let's look at the x cubed term now. So I've got 1, 2, 3, 4 minus signs. So that's a plus. Let's type those in. 0.5 times 0.5 times, and 3/2 is 1.5 times 0.5 cubed divided by 3 factorial, which is equal to 1 over 128 x cubed. And this expansion will go on forever. So let's have a look now at how to deal with ones where the number at the front isn't 1. So subheading, expansions where the constant term isn't 1. So basically a couple of notes. I'll make these available for download after the lesson as well. So when the constant term isn't 1, and an example of that, again, not wanting to patronize you, but will be that there. Then the given binomial expansion formula. Doesn't work. It must be 1 for that formula to work. We can make the constant term 1 by factorization. So let's take that example, e.g. expand 2 plus x to the power of minus 2 up to and including the x cubed term. So 2 plus x to the minus 2, we're not ready to expand that yet because the number at the front isn't 1. The formula only works, as I said before, when the number is 1. So if we take out a factor of 2, that becomes 1 plus x over 2 to the power of minus 2. However, that's not the full story because in the bracket, that 2 is still enclosed by a power of minus 2. So when we factorize and take out the 2, we're not just taking out 2, but with it comes that power. So that becomes 2 to the minus 2 equals 2 to the power of minus 2 is a quarter. And we've now got a bracket that has a 1 as the constant term. So we indeed are now ready to use that formula. So it's equal to a quarter. That's the quarter at the front of the bracket. And now we're ready to expand. So see if you can expand that. Take a moment. I'll do it in a second. See if you can do it yourself. I'll give you a minute or so on that. Okay, I'll start filling in these gaps. Not forgetting the minus sign, one of the most common errors. So 2 minus signs make a plus. And that term, just by inspection, just becomes x. 4 minus signs now. Got 1, 2, then 2 minus signs in here in the square brackets. So that's a plus as well. now at the point where I really start wanting to use a calculator just so I don't get caught out by any arithmetic errors. So 2 times 3 times a half times a half divided by 2 factorial 3/4. So 3/4 x squared. Counting the minus signs. 1, 2, 3, 4, 5. 6 rather. 1, 2, 3, 4, 5, 6. Again, a plus. So multiply that in the calculator. 2 times 3 times 4 times 0.5 times 0.5 times 0.5. I could have just written 0.5 cubed. Times 0.5 cubed, yeah, let's go with that. Divided by 3 factorial equals 1/2. Plus 1/2 x cubed. And there it is there. And we should really now multiply out that factor of 1/4 to get 1/4 plus 1/4 x plus 3/16 x squared plus 1/8 x cubed, all positive. So that's how to deal with brackets where the number isn't 1. Now let's have a look at another concept in binomial expansion, and that is the validity of the binomial expansion. We'll just write this down. Again, the notes are downloadable at the end of the lesson. The general binomial expansion is only valid for suitably small values of x. This is because the binomial expansion is an infinite series and if we sub in an x too large, the increasing powers in each term will cause terms to get bigger, thus the expansion will have an infinite value. So if we go up to one of the previous examples we did, let's go right back to the start. Let's have a look at this one here. So So take that all the way down here. Notice here, if we sub in, let's say, x equals 10, then this term is 1. This term is minus 40. 10 squared becomes plus 120. 10 cubed is 1,000 times 32. The terms in size are getting bigger and bigger and bigger, and this isn't going to settle to a constant value the more terms we add. So x equals 10 would lead to the x terms getting bigger as the power increases. Therefore, the series would not converge, i.e., it wouldn't give a nice value. It would keep going up to infinity. The series would not converge, and the word for not converging is diverging. It would diverge. However, if we subbed in x equals 0.1, say, and x equals 0.1, every time we increase the power, 0.1 squared would be 0.01, 0.1 cubed would be 0.0001. So, in fact, every time we increase the power of x, the terms get smaller. So x equals 0.1 would lead to terms getting smaller each time. Therefore, the sequence would converge, i.e. settle to a constant value the more items we add on, because by the time we get to 0.1 to the power of 20, that's so small that it's insignificant, and eventually as the powers increase, the terms that we're adding on will be closer and closer to 0, so in effect we're adding less and less on as the terms progress. So let's have a look at what actually the condition is for these sequences to converge. So for 1 plus x to the power of n, or for that matter, 1 minus x to the power of n, the binomial expansion converges as about right sequence, but same thing, but let's be more specific. Binomial expansion converges if the modulus, the size of x, is less than 1. So for example, the series expansion of 1 plus 2x to the power of minus 2 converges when the modulus of the x term is less than 1. Dividing both sides by 2, that gives me the modulus of x is less than 1/2. That sequence converges, i.e. is valid for mod x less than 1/2. E.g., 1 take 7x, the power of minus 3, is valid for modulus of minus 7x is less than 1. Now, the modulus of minus number is the same as the modulus of that number. Remember, modulus makes things positive, which means that modulus of x is less than a seventh. So the binomial expansion for that is valid when modulus of x is less than a seventh. Let's make it slightly more difficult again. Let's use a bracket without a 1 at the front. Let's say 4 plus 6x to the power of a half is valid when, in this case, the modulus of 6x is less than 4. So this rule works when there's not a 1 at the front as well. And that means that modulus of x divided by 6 is less than 4/6, which means that the modulus of x is less than 2/3. So it's only valid for certain values. So let's have a go at another example here. So find the first 4 terms in the series expansion ascending powers of x of each of the following and state the set of values for which the expansion is valid. So let's try this one here. Now this is a bit different than before. So it says 2x minus 1 over 1 plus 4x squared. So in a question like this, what you'd be expected to do is, rather than write it as a quotient, actually write it as a product. So 2x minus 1 times 1 plus 4x to the power of minus 2. And this bit here is the bit we need to expand. And then after we've expanded it, it's asking us to multiply by 2x minus 1. So let's try and expand 1 plus 4x to the minus 2 here. So you have a go at expanding that first. I'll come to it in just a moment. I'll probably give this a bit more room. Bring it down there. So that there equals 2x take 1 times, and that's the first 4 terms, 1 term, 2 terms, 3 terms, 4 terms. So count the minus signs, 2 of them, so it's a plus. And then rely on the calculator. 2 times 3 times 4 squared divided by 2 factorial is 48 x squared. Count the minus signs. Got 1, 2, 3 there, so it's a negative. So 2 times 3 times 4 times 4 cubed divided by 3 factorial is 256 x cubed. And then we need to expand the bracket again. So times them all by 2x and by minus 1. So we've got 2x minus 16x squared plus 96x cubed. Take 512 x to the power of 4. Then times them all by the minus 1. Take 1 plus 8x. Take 48 x squared plus 256 x cubed equals so we've got minus 1 at the front. I'll put a little mark under it when I've used it. Then we've got the x terms. So I've got 2x plus 8x, which is 10x. So positive 10x. Then the x squareds. So minus 16x squared minus 48x squared. That gives minus 64x squared. 96 and 256. 96 plus 256 is 352 x cubed. And there's an x to the 4 there. However, it's only asked for the first 4 terms. So I've got the first 4 terms of the expansion. Next to the 4 would be the 5th term. So we'd ignore x to the 4 on the grounds that it would be so small when we sub in a valid number that it's ignorable. But it's also asked for the values of x for which the expansion is valid. So this is the binomially expanded part. So what we're going to have to do is state the domain of validity, which is valid when, so mod of 4x is less than 1, which means that mod of x is less than a quarter. And that's that example done. If you asked to do the binomial expansion for something like this now, make it even more difficult. There's a certain method you could use for this one, because currently we're not really able to do it because both terms are in the denominator and are currently inseparable. So we need to find a way to separate them. And the method we're going to use is partial fractions in order to separate them. So let's go for that. So 4 over 1 plus x, 1 minus 3x is identical to, I'm going to go a over 1 plus x plus b over 1 minus 3x. And then, as we saw last week, multiply by the denominator on the left-hand side, which means that 4 is identical to a times the 1 plus x is cancelled to give 1 minus 3x, plus b times, and the 1 minus 3x is cancelled to give 1 plus x, like that. And if we sub in a value, So let's say let x equal -1, a tactical value that's going to make one of the brackets disappear. X equals -1, which means that 4 equals a bracket, and it's 1 minus -3, because 3 times -1 is -3. So 4 equals a times 1 minus -3, which is 4. Which means that a equals 1. Then x equals 1/3 for the other bracket, which means that this first bracket disappears. So we get 4 equals, and b times 1 plus 1/3 is 4/3 b, which means that 4 divided by 4/3, b equals 3. Therefore, concluding, we've got a over 1 plus x plus b over 1 minus 3x. And there's our expansion, or expression rather, ready to expand. So I'm going to call this expression A, and I'm going to call this one expression B. So that's our first expression to expand. And once we've done that, we can expand the second. So have a go at that. Take a moment yourselves. So again, this is an example of when partial fractions can be used to separate out expressions and make them binomially expandable. We'll stick to the first 4 terms up to including x cubed. So that's the first one. The second one can be rewritten like that. So it's 3 lots of whatever we expand it to be. So 1 over 0 factorial plus n x term to the power of 1 over 1 factorial plus n minus 1 x term squared over 2 factorial plus n minus 1 n minus 2 x term cubed over 3 factorial simplifying 1 plus 3x Let's start getting the calculator for these now. So there's 4 minus signs, so that's also a plus. So 1 times 2 times 3 squared divided by 2 factorial. 9 x squared. There's 6 minus signs on the next one, so plus 1 times 2 times 3 times 3 cubed divided by 3 factorial. 27 x cubed. And finally multiplying out the 3, I get 3 plus 9x plus 27x squared plus 81x cubed. And that's that one done. So now we're being asked to add a and b together. A plus b. So let's do that. A plus b equals, so the number term is 4. The x term, minus x plus 9x, is positive 8x plus 28x squared plus 80x cubed. And now we're done. That's it. So there's loads of different types of questions you can have a go at on the worksheets that I've put in the live lesson area. So have a go at those. And if you do, you'll have basically nailed all of binomial expansion. So there's a vast array of different types of question there, all with fully worked solutions. So you can have a go at those. That's really all I've got for you, because binomial expansion doesn't really go much further than this. So that's it for today. So it'll be another one. Next week is half term, so there won't be one next week. We will resume the week after, which is the Saturday before you go back to school after half term. So next week, no lesson. The week after, lessons resume. So no lessons on the first Saturdays of half terms. So have a good week. Enjoy.